Numeric solutions. Numeric solutions are mainly used when there is no analytic solution, where there are infinite solutions such as redundant robots, or when it is too complicated to find a solution. The idea is the following. We have forward kinematics given by this expression, and then we try to reorder the terms so that we have something equal to 0. And basically we want to find the Q using iterations such that this difference is 0 or close to 0, or such that we minimize this difference or the norm of this difference. To do that, both methods that we are going to see use the Jacobian matrix, which is just the analytical Jacobian in robotics. N is the size of Q, M is the size of X, and so the Jacobian will be in N times M. Usual solutions methods are the Newton's method and the gradient descent method. We will see both of them. First, let's see the Newton's method. The Newton's method is basically a root finding problem. So given a constant x desired, we want to find Q such that this equation holds. If you see here, we want to find the Q that makes this expression equal 0. So we are writing this as a root finding problem. The procedure for the solution is the following. First, we obtain the first order Taylor approximation for this f. This is the first order Taylor approximation, where this J is the Jacobian matrix, which is just the derivatives that you have seen in calculus courses. Now we replace this f into this expression here, and we obtain this new expression. We reorder the terms, and we put here xd minus fk, and then we reorder this, we put this j on the other side of the equation, and we can assume that j is a square and invertible, so that n equals m, so the inverse exists. So this j goes to the other side with the inverse, and now we solve for this q, and we see that this q here is going to be the new q, so this qk is going to go to the other side. So finally we will have this qk to the other side, which is this one, plus all this term, which is this one, and this is the expression that we want. So at the end, Newton's method consists in implementing this expression. The algorithm will be the following. We start with an initial Q0, which is usually the current configuration, and we iteratively update using the previous expression, which I repeated here. And we stop when either we are too close to the real x desired, that's to say we have a small Cartesian error, or we're not increasing too much the joint, so probably we already converged. So there's a small joint increment. We can use any of them, both of them. Sometimes it's preferred to use the small Cartesian error. Now convergence is guaranteed if we start with Q0 with some initial value close to the solution. When there is redundancy, then J is not going to be squared, and so there will be no inverse. In these cases, what we do is we use the pseudo-inverse. The disadvantages are that the computation time of the inverse takes some time, or the pseudo-inverse, it's not that straightforward, it takes some time. And there are some problems near singularities of J, the Jacobian matrix. The advantage is that it is fast. It has quadratic convergence, which means that it is fast. I'm not going to discuss quadratic convergence, but it is a desired property for an algorithm. Let's see an example. This is the same example that we have been seeing before, but now we have to do it numerically. To deal with it numerically, we have to assume that L's have some value. In this case, we will assume that L1 equals L2 and that equals 1, and we want to reach this position, 1.2, 1.2. The end effector should be there. So for the solution, the desired position is this one, 1.2, 1.2. We have forward kinematics. We need the Jacobian, which is the expression. We are going to compute now the Jacobian analytically. Just take the derivatives. We will obtain this. You can verify this later. And we need the inverse of the Jacobian. You can also do this analytically or later numerical. We're doing this in this case analytically. The expression for Newton's method is this one. We are just replacing the values. We computed this Jacobian inverse, which is this term. The x desired is this 1.2, 1.2, and the forward kinematics is this expression. This is the current error as well. So this is iteratively applied using some software. For example, we can use Q1 equals 0.5 and Q2 0.5 as initial values. Note that we cannot start with Q2 equals 0, because in that case we would have 1 over 0, and that would make the Jacobian, the inverse of the Jacobian, not to exist. This is a Python code that implements the previous algorithm. Note that the result depends on the initial value. So if we use as initial value 0.5 and 0.5, this will be the result. But if we use 1 and minus 1 as initial values, we will get this result. You can see that in both cases the end effector is at 1.2, 1.2, but the solutions are different. Both solutions are equivalent, but they are closer to the initial point. The other method is the gradient descent, but first let's see the generic gradient descent. In general, the gradient descent consists in minimizing a generic function g of q. We want to minimize the g of q, and the idea is to start with an initial guess, q naught, and then we move in the negative direction of the gradient, because the gradient indicates the direction of maximum variation, but we want to minimize, so we move in the negative direction of it. That is, the new q that we have is going to be the previous q minus the gradient, but with some alpha, which is called the size of the step. Something that we have to take into account is that this step size must guarantee a maximum descent in every iteration. If this is very high, it can lead to divergence because the minimum won't be found. And if it is very small, it will generate a slow convergence. So we have to be careful when choosing the value for alpha. Now we're going to apply this gradient descent method to inverse kinematics. Forward kinematics is given by this expression, or equivalently this. And we can consider this as an error. The procedure is to define a scalar error. In this case, we can take the norm, the square norm of this, and put just 1/2 for mathematical convenience. Then the objective will be to minimize this error, this function, the norm of this error. We compute the gradient of this q. In this case, this expression is exactly the same as this one, but written in a different way. And the gradient analytically would be something like this. So we take the derivative of this, it's just the same expression, and then the derivative of whatever is inside here. This is a constant, so it will be the derivative of this j with a minus, which we have here, the minus derivative with respect to q. And this is called the Jacobian again. And we apply the gradient descent algorithm. If we replace the previous elements, we just get qk and then alpha and the gradient, which is this one, and we get this expression. And this is our basic equation for the gradient descent method. The pros are that it's computationally simpler because it's easier to compute the transpose instead of the inverse. And the cons is that it can have a very slow convergence depending on the value that we choose for alpha. Consider again the same example that we have been seeing before with the same desired position. In this case, we again have the forward kinematics, we have the Jacobian analytically computed, and now we don't need the inverse, just the transpose. We're going to again just replace in the generic expression here, where this is the current error, and that's the way that we will solve. You can do this manually, but usually you do this in a computer. For example, if we use again 0.5 and 0.5 as initial values, we can obtain some solution. In this case, we can start with q2 equals 0 because we have no inconsistency with this value. If you remember, in Newton's case, we could not do this because the inverse of the Jacobian would not exist. In this case, it does exist, so it's more robust in that sense. This is the Python code that implements it. You see that here we have the Jacobian and here we have the Jacobian transpose, so I didn't need to do it explicitly. You can do it if you want, but this expression will work. The comparison is the following. Newton's method has quadratic convergence rate, which means that it is fast. The gradient descent method has a linear convergence rate, which means that it is slow. In Newton's method, there are problems near singularities. Singularities can be computed using the singular values. In the gradient descent method, there are no singularity problems. Also, in gradient descent, the step size must be carefully chosen. However, there exist adaptive methods such as line search for wisely choosing this alpha. We are not going to see that, however. An efficient algorithm consists in first starting with the gradient descent method because it's safe but it's slow, and then switching to Newton's method because it is not too safe close to singularities, but it is fast.